Hello, chemistry students. We're here to do lesson 11.6, where we take a look at the pH scale.
Our first objective is to define and calculate pH and pOH.
And we are going to determine the relationship between the pH of an acid or base and the pOH.
We're going to use the Kw value, which is a constant, to determine the concentration of an acid or base.
And also take a look at how indicators are useful in chemistry, especially in acid-base chemistry.
Yep.
Let's get started.
So, the first thing we're going to talk about are indicators, and these are a substance used to determine the relative acidity or basicity of a solution, generally through a distinct color change. We have a lab this year that deals with a lot of indicators to give you an idea of what an indicator can be used for and how they show up.
Okay, so this just shows you, the range of different indicators that are out there, and this is by no means a complete list. You can see they all have different pH ranges that they work in, and so they can be useful in different situations to let you know what you're dealing with. The color change that occurs, we can see, for example, bromethymol blue, okay, is going to go from a yellow color to a blue color at just about 7, which would be a neutral pH. So if you're trying to neutralize base with acid, neutralize acid with base, you could choose that one as an indicator.
Mm-hmm.
Okay, neutral red, similar kind of color changes, slightly higher pH, but we have this whole sort of toolkit of indicators to draw on in chemistry to give us an indication of where we're at on pH.
Yeah, and these are most useful in a method called titration, which is another lab we're actually going to get to today. And let's go on and discuss what titration is. Okay, so shown below here is a titration setup. Titration is when you use a solution of known volume and concentration to determine the concentration of an unknown solution. So the first thing you have to do is what they have pictured here is known as a volumetric pipette, meaning it delivers as accurately as possible 20.0 milliliters of a known concentration acid solution. They then put that acid solution into the flask here, and they have a known concentration. Sorry, I was wrong.
Yeah, the acids are unknown.
Yes,
we
the
don't
acid
know
was
what,
the unknown.
what the pH of the acid or how concentrated the solution is.
Wow, yeah. Because then the sodium hydroxide is known as the standard solution, which is the one that has the known concentration.
This is right mixed up. We know what the pH and the concentration is, and the burette is, what's that for?
The burette is filled up, and it has gradations on the side that tell you what your initial volume reading is. And then throughout the titration process, the volume, of course, will lower. And you will see that at the very end, your indicator will change a color, which will signify that your titration is complete. And at that point, you record the final volume here. And the difference between the initial and final volume tells you the amount of your base that was delivered. And from that, since we know how to use molarity, we can we can calculate the concentration of the acid through that reaction.
Yeah, which then it turns into a reaction stoichiometry problem. So we know, the amount of this reactant, and we can use that to find our molar amount, and then the pH and concentration of the unknown, which is the acid. So it sounds a lot more complicated than it actually is. We can graph pH versus volume of material added. It gives a real interesting graph. We'll be doing that as well. But so that's just a little foreshadowing of what you can do if you understand the idea of pH and acid and base concentration. Let's move on, and we'll take a look at the pH measurement itself now.
So go ahead.
Okay, so what is pH? I mean, we already are familiar with the pH scale, and I think numbers, and we know that numbers below 7 are acids, and above 7 is base, and 7 is neutral. But it actually is a mathematical calculation. We can calculate it, and it's based on the concentration of certain ions. So if we look at the first equation here, pH is the negative logarithm to the base 10 of our hydrogen ion concentration, or we can think of it as the hydronium, the H3O+, kind of the same thing. Okay, so that's where the actual pH number comes from. The pOH, then, which is kind of the anti-pH, is the negative log of the hydroxide ion concentration. And the cool thing about these two, for any solution of water with anything dissolved in it, the pH plus the pOH of that liquid always adds up to 14. So it's kind of a constant, and we'll take a look at mathematically why that is when we get to our KW. Let's try an example problem of each type.
All right, so shown above here is a question about pH, and they're asking what is the pH of a solution that has a concentration of 1.0 times 10 to the negative 6 hydronium ions. They then want to know what the pOH of this solution is as well. So first of all, we use the pH equals the negative log of the concentration given to us, and we find that it simply equals 6. So this solution is only slightly acidic. Now to find the pOH, we would have to take pH plus pOH equals 14. You would plug in the pH is 6, and we would take 14 minus 6 and find that the answer is 8. So that's just telling you that the solution is not basic because the pOH scale is similar to the pH scale.
Except
that,
backwards.
Yes, exactly. For the pOH scale, 1 is basic and 14 is acidic. For the pH scale, 1 is acidic and 14 is basic. So it's just kind of reverse thinking.
Okay, let's move on to the second one. So now we're going to work it backwards. So we have this solution that has a pH of 3. And we're going to work backwards to find out what is the concentration, the molarity of the hydronium ion in the solution. So remember our basic formula, the pH is the negative log, that is the negative power to the base of 10 of the concentration. So substituting in, 3 is our pH, is equal to the negative log of the hydrogen ion concentration. And then we have to rearrange it, and what we're saying is that the concentration of hydrogen is 10 to the negative 3 power. Okay, which would be 0.001 molar.
Now, for those of you wondering why we have to use 10, if you haven't had this in math class yet, this log is to the base of 10. So to get rid of it, you have to raise both sides to the 10 to make sure that goes away. So that's your math lesson for today.
And we will work on this more in class. There's buttons on your calculator that can do all of this stuff. We picked really simple ones here where the coefficient is a 1. It's not always a 1, so that
changes things.
Changes how you have to maybe handle it on your calculator a little bit. But it's really simple. If you understand how to use your calculator, doing it backwards, like to work back to the concentration, is not really difficult. It's a few keystrokes on the calculator.
So there's something in chemistry similar to what we already talked about for acids. There's something called autoionization. And this is when the same reactant acts as both an acid and a base. And we have seen this before in acid bases. We had ammonia, which could act as both the acid and the base.
Right.
So this case is also water. And since water is the most abundant solvent on the planet, we kind of base everything around it. And what we're going to talk about is this ion product constant for water, which is known as KW. So we have to know that the ion product constant is KW, little w, yep. And that is the product of the hydronium ion and hydroxide ion concentrations in the autoionization of water. At 25 degrees Celsius, this is equal to 1.0 times 10 to the negative 14th. So,
I don't believe there's any unit on that.
It's the concentrations of. But, so we can use this now for any acid or base reaction that is done at 25 degrees. The constant here is temperature dependent and changes with the temperature. So if one is given to you at a different temperature, they would also give you the new KW value. So we know that the KW is 1.0 times 10 to the negative 14th. And through that, we know that the concentration of the hydronium ion times the concentration of the hydroxide ion equals 1.0 times 10 to the negative 14th, which is a very powerful tool if you know the pH of the solution You can then calculate the hydronium concentration or the hydroxide concentration of anything in water at this temperature. So it's a useful gadget for figuring out concentrations of hydronium or hydroxide in your solution of water.
And just for example, like when we say autoionization, like if you just take absolutely pure water at 25 degrees Celsius, it autoionizes. That is, it automatically, a small amount of those water molecules are going to break apart into hydroxide and hydrogen ions. Okay, and the concentration of pure water is 1 times 10 to the minus 7th, okay, hydrogen ions. So that's 1 times 10 to the minus 7th moles of hydrogen ions produced per liter of solution at 25 degrees Celsius, which would mean an equal amount of hydroxide ions, okay, times 10 to the minus 7th, which is going to give us 1.0 times 10 to the negative 14th. Okay, but what's interesting is when an acid, we have a solution that's acidic, this number goes up, this correspondingly goes down, and so it doesn't matter whether we have an acid or a base, the product of the concentrations of hydrogen or hydronium and hydroxide is always this constant.
Yep, at 25 degrees.
At 25 degrees.
So shown here is just a pH scale. We haven't really shown you one and really talked about it, but most of you seem to already understand that if you're lower than 7, you're looking at an acid. If you're higher than 7, you're looking at a base. And there are some things written below here that tell you what they are. At 0 is hydrochloric acid, and then as we keep going up the scale, you have upset stomach acid, which means, stomach's full of acid. You have normal stomach acid, you have vinegar and orange juice, and, all these things that you use in a daily life. And then as you go up towards the base side, you have a lot of things we no longer eat, except for eggs. We have like detergents and borax and ammonia and bleach and sodium hydroxide. These are things we don't eat. So humans don't really eat bases.
Other than really, really slightly basic. But we do like things that are kind of in this mild acid range in here for a lot of our foods.
All right, so here are 2 questions for you to work on tonight. They want to know what the concentration of H plus of a 3.4 pH solution, assuming 1 liter, and then assume that the solution above is at 25 degrees Celsius. What is the concentration of hydroxide? Use the kW to solve this problem.
Or you could use POH.
POH
and work backwards from there. Either one. So I know we went through the math a little fast, but try to set these up like we did the examples, and we'll go over them tomorrow in class.
Good luck.